This lesson's about Kirchoff's rules, which are going to allow us to solve more complex circuits. First, Kirchoff's junction rule, which states that the total current into any junction equals the current out. So here's a junction, a meeting of wires, and if we have a current in, let's call that I1, and two currents out, I2 and I3, then the junction rule states that I1 must equal the sum of I2 and I3. Anything going into a junction has to leave, and this follows from the law of conservation of charge. There's no place else for the charge to go, charges can't bunch up, so anything into a junction has to leave. That's Kirchoff's junction rule. Kirchoff's loop rule states that the sum of the potential gains and drops around any closed loop has to sum to 0. So what does that mean? Here's a series circuit, and let's say this is a 9-volt cell, and these are two resistors. We'll say this is a 1 ohm resistor and a 2 ohm resistor. The job of this 9-volt cell is to raise the potential energy on the charges. It's giving 9 joules to every coulomb of charge. And that energy has to be dropped at the two resistors. And it's going to be dropped in proportion to their resistance. So for example, if this is a 1 ohm and a 2 ohm resistor, then we'll get a 3 volt potential drop here and a 6 volt potential drop over here. If they were instead equal resistances, let's say this was a 1 ohm resistor and this was a 1 ohm resistor, then we'd get 4.5 volts dropped at each. But in either case, all of the energy given at the cell has to be shed as you go around the circuit in order to get back to the bottom of this staircase, if you want to think about it that way. So the sum of the potential gains and drops around any closed loop has to be equal to 0. Here we've just got one loop. We're going around like that. Here we have a parallel circuit, and now we actually have several loops. We've got this loop here. We have this loop around the outside through the bottom resistor, and we actually have a third loop right here, which we could use. And what the loop rule states is that the sum of the potential gains and drops around any of those is equal to 0. So here, let's say this is a 9-volt cell again. Whatever the resistances of these two resistors are, they're going to experience the full 9 volts of the cell. Again, the cell's job is to raise the potential energy of the charges, and all of that has to be shed at each of these resistors. And because as you go around the green loop or the red loop, you only go through one resistor, to get back to the start here, you have to shed those full 9 volts. So Kirchoff's loop rule says that the sum of the potential gains and drops around any closed loop has to be equal to 0, and this follows from the conservation of energy. Again, to go around the circuit, you have to get back to the starting position or the starting point of energy. And because energy is not created or destroyed, any energy gained at the cell has to be shed at the resistors or the loads. So that's Kirchoff's junction rule and loop rule. Now let's see how they can be applied to help us solve circuits. So here we're looking at a simulation from PhET. The URL is here at the top, and I've got a circuit with a 4 volt and a 12 volt cell and a 4, 10, and 2 ohm resistor. And my question is, what are the currents in this circuit? So here now is a diagram of that circuit. I've filled in the values, and we're going to follow these steps to apply Kirchoff's rules. So first, we're going to mark the ends of each cell positive and negative. Positive is the long terminal, negative is the short. Now I'm going to label each current, and I'm just going to name them. So I'm going to call this current 1, and I'm going to say that it's going in this direction. I'm going to imagine that because this is the positive end of the cell, but I don't actually know. I'm going to call this current 2. By the way, if this is current 1, then there must be current 1 over here, because this has only one path, so there's only one way for the charges to be flowing. And similarly, current 2 must be down here like this. Again, I don't know that these are the directions of the current. I'm just going to put them in arbitrarily. This is a third current over here. I'm going to imagine it's going in that direction and label it I3. So I've done this. I've labeled each current, and I've actually already chosen a direction for each current, and that's arbitrary. These might end up being the wrong directions for these currents, and I'll see that later. Now, once I've got the current, I can mark the ends of each resistor positive and negative, because remember, conventional current is going from high potential to low potential. So if the current is going this way, that makes this the positive and this the negative end of this resistor. Similarly, this would be positive and negative, and over here, this would be positive and this would be negative. That's defined once we say which way the current is going. Current is flowing from high potential to low potential. And now I'm going to label key points in the loop. So I'm going to call this corner A, this is going to be B, this junction I'll call C, D, E, and F. And I'm going to do that just so that I can show my work carefully and label things. Now I'm going to write down equations for each junction. So at junction C, and this is the junction rule, at junction C, I have I1 plus I2 equal to I3. I1 and I2 are coming into junction C, I3 is leaving. If I look at F, I have the same thing. I have I3 is equal to I1 and I2 that are leaving. So this would also apply at junction F. Those are the only junctions I have, so I'm done with the junction rule. Now I have to apply the loop rule. So to do that, I'm going to pick a point and I'm going to go either clockwise or counterclockwise, and I'm going to use signs to indicate my voltage gains and drops. Let me show you what I mean. I'm going to try and squish the first one in here so that you can see it all on the screen at the same time. Let's look at the loop starting at A, going around here, the top loop, and back to A. So that's going to be loop A, B, C, F, and back to A, and I'm going to go like this counterclockwise. Now, if we start from A, we go first through a 4-volt cell, and we're gaining potential as we go from the negative to the positive end. Then we go through a 4-ohm resistor, and we are decreasing potential. We're dropping potential, dropping energy as we go through this. Then here there's nothing happening, there's no resistance in the wire. Then we go through this resistor, and we are again experiencing a drop in potential, and then coming back to the start. So if I write out an equation with only potentials in it, only voltages, I get the following. I have a 4-volt potential gain here. Then I have a potential drop, and that potential drop is equal to current I1, because that's what I have here at the top, current I1. I have current I1 multiplied by that 4-ohm resistance. This is of the form IR. And remember, IR is equal to V. The potential drop at a resistor is equal to the current through that resistor multiplied by its resistance. So that's why I have this form. So I have a 4-volt potential gain here. I have whatever I1 is multiplied by 4 ohms, the potential drop here, nothing over here. Here, by the same kind of reasoning, I have a potential drop of I3 multiplied by 10 ohms, and then I get back to the start, and the loop rule tells me that that has to sum to equal 0. So if I simplify that, I get 4 minus 4I1 minus 10I3 is equal to 0. You can see now that we're starting to build up a system of equations. Right now we have 2 equations with 3 unknowns, so we're not done yet. We won't be able to solve, but that's what we're doing. So now let's do it again, choosing another loop. We're going to choose a loop that'll help us illustrate some more points. So we're going to start here at A, and we're going to go this time clockwise around the big loop like that. Okay, so what that means is that we are going to do loop A, E, D, B, A, and we're going clockwise like this. So if you take a look there, what we're doing first is we're going through this 12-volt cell at the bottom, and we're going through in the forwards direction, so that's a 12-volt potential gain. And then we're going through this 2-ohm resistor with current I2, so that's going to be a drop of I2 multiplied by 2 ohms. And then we go all the way up to here, and notice here we're going backwards through this resistor. So the current's going this way. This is the positive and this is the negative end. So if we were going to the left through it, it would be a potential drop, but we're actually going through the right. So you have to be careful not to mix up the current direction and the direction you're moving around the loop. We've set the current as being here red from right to left. We're going in the green around the loop from left to right in the opposite direction. That's why it's helpful to have these positives and negatives that we've put here, because we can see that if we're going from negative to positive through this resistor, it's actually a potential gain. So we have a potential gain of I1 times 4 ohms. So that's our next bit. We have a potential gain plus, right, that's a positive because we're going backwards through the resistor relative to the current, of I1 multiplied by 4 ohms. And by the same reasoning, now we're going backwards through this cell. When we looked at it in the previous loop, we were going from the right to the left. That was a potential gain. Now we're going from the left to the right. That's going to be a potential drop. So we're running through the cell backwards. So now that's negative 4 volts. And now we've completed the loop, gotten back to the start, so the loop rule tells us that that sums to 0. Now if we collect our like terms, we get 8 minus 2I2 plus 4I1 is equal to 0. Now we have 3 equations with our 3 unknowns, and we can plug those into an equation solver on our calculator or on a computer, and we can solve. And we would get an answer of I1 is equal to negative 1.06 amperes. I2 is equal to 1.88 amperes, and I3 is equal to 0.82 amperes. Now, what does this negative mean? That negative means that when we chose the direction for I1 up here, and we arbitrarily said that it was going this way, right to left, and therefore down here and up here, we actually got it backwards. And so it's actually the other way around. I1's got to go that way, it's got to go this way, and it's got to go this way. The other ones, we just happened to choose the right direction. But for I1, this negative here tells us that we had gotten it in the wrong direction initially. Here we are back in our simulation, and if I show the current, we can see the current's going in the directions now that we've found. It's going from left to right up top. That's why we got our negative when we had initially chosen that it was going from right to left. Elsewhere, we got it correct. And if I check our currents, we get 1.88, we get 0.82, and we get 1.06. So we can see that we solved for the right answers. Just one more thing, we only needed this many equations to solve, but you also could have used loop F, C, D, E, and back to F, and let's say we went through that counterclockwise. So here we're starting in this small bottom loop and going around like that. And if you did that, if you wanted to check your understanding, you'd see that you get 10 times I3 plus 2 times I2 minus 12 is equal to 0. And you could have used that as one of the equations as well. So that's Kirchhoff's rules and how to use them to solve more complex circuits.